Hello everyone, thank you for watching this video. My name is Keir Rogers. I'm a Dunlap Fellow at the Dunlap Institute, which is at the University of Toronto. And I'm going to be discussing in this talk work which has been searching for axion dark matter, which is a well-motivated particle candidate for the dark matter, using the Lyman-alpha forest, which is an absorption feature we see in the spectra of high redshift quasars, and it's a very sensitive probe of the nature of the dark matter. So the search for dark matter is an opportunity to discover new physics which may deepen our understanding of nature. And the preferred candidate over the last few decades, the weakly interacting massive particle, has continued to not be detected at colliders and direct detection experiments. And in parallel, in the last few years, a lot of focus has been shifting to alternative, theoretically well-motivated paradigms, in particular axions and axion-like particles. But their parameter spaces today remain largely unexplored. And in this work, we use the Lyman-alpha forest, which is very sensitive to the distinctive phenomenology of a class of axion-like particles called ultralight axions, very low mass particles, typically on the order of 10 to the minus 22 electron volts. And in particular, they induce a sharp cutoff in the linear matter power spectrum, which we can use the Lyman-alpha forest to look for. And I will discuss elements of the analysis, in particular the construction of what's called a Bayesian optimized emulator, which is a way to use hydrodynamical simulations in an efficient manner, and also to test for convergence in your estimation of posterior distributions with respect to your modeling of the data. And at the end of the talk, I can present new bounds that now significantly rule out this canonical range of masses for ultralight axion dark matter at 10 to the minus 22 eV. So axions and axion-like particles in their simplest formulation generically have potentials as illustrated on the left of this slide with a sort of hat-shaped potential. And as the universe cools, symmetries break and the field will oscillate in this potential minimum, and energy is stored in these oscillations that can be quantized as axion-like particles, and these are viable dark matter candidates. And these are generically produced in many beyond standard model theories. In particular, in string theories, we have the prediction of what's called the string axiverse, the idea that we have many different axions, each of different masses, and that one or more of these could be the dark matter. And there's been some recent work suggesting from a combination of theoretical considerations and current experimental constraints that there may be a preferred mass scale within the axiverse to be the dark matter on the order of 10 to the minus 22 electron volts, these ultralight axions. And the other part of the motivation for this ultralight mass regime comes from the so-called small-scale crisis of cold dark matter. And that's a collection of discrepancies between the predictions of CDM-only simulations and observations on galactic scales. And ultralight axions, being the dark matter, have been invoked to resolve the so-called crisis because their masses are so low that you would have quantum effects manifesting on astrophysically large scales. And in particular, at the centers of dark matter halos, you would have a de Broglie wavelength for an axion of 10 to the minus 22 electron volts on the order of kiloparsecs. And in simulations, you have the production of solitonic cores, and this would naturally explain the core-like density profiles that are inferred from observations of galaxies. And it has become clear in the last few years that it is paramount to model accurately the interplay of the dark matter halo with the baryonic components of a galaxy, and that many of these discrepancies are explained by including baryons in your simulations, and new data has improved our picture of the subhalo population. But we could now turn the problem around and use observations on small scales to place empirical bounds on the allowed range of ultralight axion masses. In particular, in this work, we use the so-called quantum pressure scale, which is on the order of 100 kiloparsecs. And below this scale, for ultralight axion dark matter, there's a very strong suppression in the growth of small-scale structure. And that is illustrated in this plot on the bottom right, where I have slices through simulations, on the left hand for the ultralight axion dark matter, on the right for standard cold dark matter. And you see in the axion case, much less small-scale structure, smoother filaments, and fewer subhalos orbiting the central halos. So we search for this suppression of the growth of structure as it manifests in the linear matter power spectrum. And so this plot is showing the square root of the ratio of linear matter power for ultralight axion dark matter to cold dark matter. It's a function of wave number k. And each line is the transfer function for an axion of a different mass. You see for each of them this very distinctive cutoff in the power spectrum. And in particular, as we increase the axion mass ma, the wave effects will manifest on smaller scales, and so the cutoff gets pushed out to larger values of k. And so if we want to improve our bounds on axion mass, we need a tracer of the dark matter distribution on smaller and smaller scales. And we use the Lyman-alpha Forest, which gives us the smaller scales we can currently access in the linear matter power spectrum. And it's a very good tracer of linear order perturbations because it's being sourced from intergalactic gas, which mostly resides at mean cosmic density. And so it's less affected by nonlinearities than other tracers of the large scale structure, for example, galaxies. It's also a high redshift probe. And so again, there's been less time for nonlinearities to have erased this clear signature in the linear power. So the Lyman-alpha Forest traces the dark matter distribution, but indirectly via the distribution of the baryon, the ordinary matter in the universe. And in particular, the Lyman-alpha Forest is sourced from absorption in the light of background sources by neutral hydrogen in the intergalactic gas. And therefore, the Lyman-alpha Forest, the extent to which suppression in the growth of structure from the particle nature of the dark matter is partly degenerate with the uncertain astrophysics of the intergalactic gas. And in particular, we're sensitive to the extent to which the hydrogen is ionized, and also the temperature and the pressure of the gas. And so we will need to marginalize over nuisance parameters that characterize this uncertainty. And so this plot illustrates all these fields that I mentioned, and in all of them you see the typical filamentary structure of the large-scale structure as shown in simulations. And in the bottom right, you see the Lyman-alpha Forest flux, but we do not have access to the full three-dimensional field. Rather, we see it in one-dimensional skewers through it, as indicated by the red arrow. And then in the inset, you see the data that we actually collect. So that's an example quasar spectrum. And the absorption in the quasar spectrum is a tracer of the fluctuations in the matter distribution along the line of sight to the background quasar source. And the most accurate modeling of the Lyman-alpha Forest required for robust inference requires the calculation of hydrodynamical simulations. But for the requisite numerical accuracy, each simulation takes on the order of 3,000 CPU hours, and considering all the axion and IgM and cosmological parameters we must vary, this constitutes a 12-dimensional parameter space. And so naive approaches to parameter inference, for example, running an MCMC chain to estimate a posterior distribution, where you would want to run a new simulation for each step in that chain for a different parameter combination, are not feasible. And so instead, we're going to construct what's called an emulator, which is a way to take a few simulations that you are able to run that we call the training simulations, and effectively interpolate between them such that we have a global surrogate model for how a simulation behaves throughout the parameter space. So for the next section of the talk, I'd like to illustrate how this emulator works using a one-dimensional toy model. So if we start at the top panel, we're going to have a function, which is the blue dashed line, which has a single scalar output as a function of a single parameter value. And this is a proxy for the power spectrum of the Lyman-alpha forest as a function of all the input axion and IgM parameters. And we want to estimate the blue dashed line, which is the true function, but we only have information at the black crosses, the training points. And to do the emulation, we're going to use what's called a Gaussian process. And that's just a way to smoothly and probabilistically interpolate between the training simulations that we have. So we fit the Gaussian process to the training data, which is to say we train the emulator, and we then use it to make a prediction as to what the true function is. And the red line is the mean of that prediction, and the red band indicates the 1 sigma uncertainty. And you see that the uncertainty is low, near where we have training information, and it increases as we move away from where there is training simulations. And we can then use that to do a likelihood analysis. So in the bottom panel, the blue dashed line shows the likelihood for some mock data if we knew the true function. And the red line shows our estimation of the likelihood, given that we only have the emulator prediction. And you see that the consequence of having uncertainty in your emulator is to broaden the peak of the likelihood. And so we'll have weakened parameter constraints as a consequence. So the key idea now becomes how best to decide where to run these training simulations such that we have accurate determination of the peak of the posterior distribution, i.e. the 95 to 99% credible region that we are interested in. And we're going to use an idea called active learning, which is to iteratively build up the training set until we have converged estimation of the posterior distribution with respect to the emulator model. And so at each iteration, we will use Bayesian optimization. In particular, we define an acquisition function to decide where we should add the next training points. So in the bottom left panel, you see the acquisition function for that iteration. It balances two things. It peaks where the emulator uncertainty is high, so that we have a better global precision in the emulator. But it also peaks where the likelihood or the posterior probability is high, such that we tend to concentrate resources in the parts of parameter space that the data prefer. And we don't waste adding lots of simulations away in the tails of the distribution. So we find the maximum of the acquisition, we add a training point at that position, we retrain the emulator, we get more accurate determination of the objective function, and that propagates to more accurate determination of the likelihood function and the posterior distribution. And we iterate this process until we have converged estimation of the posterior with respect to the addition of further training points. So that's an illustration on a one-dimensional toy problem. And we then did a test on mock Lyman-alpha forest data using an IgM and cosmological model. So this plot is showing a set of marginalized posteriors for mock data where the black dotted line shows the true simulation values. And there are two sets of contours. The red contours are for the case where we don't use the active learning in the construction of the emulator, and the blue contours are where we do turn on the active learning. And then the crosses show the projected positions of training simulations, color-coded by the version of the emulator to which they contribute. And if we concentrate on this inset, you see that the consequence of using active learning is the addition of these blue training points, and these tend to be concentrated at the peak of the posterior distribution, so we don't waste adding lots of simulations away in the tails. And the consequence is to reduce the error in the emulator locally at the peak of the posterior, and that contributes to more accurate posterior determination and tightened parameter constraints as a consequence. And we can do that using fewer simulations than the brute force approach of just adding more evenly throughout the full parameter space. So we tested that on the specific example of Lyman-alpha Forest data, but emulators are being constructed for many other analyses of the cosmic large-scale structure, which rely on the use of n-body simulations. And here I have an incomplete list of the various examples, statistics, and traces that they have been applied to. And all these emulators could benefit from the idea of using active learning to construct the emulator training sets in an efficient manner, such that we're able to get a sufficient accuracy in determination of statistics of the large-scale structure for next generation surveys. So for the final part of the talk, I will present how we applied this emulator methodology to the problem of inferring the allowed range of ultralight axion dark matter masses using the Lyman-alpha forest. So this plot shows the results of applying it to real data. So again, it's a set of marginalized posteriors, this time for the axion mass, which is the parameter on the far right. Then we have the various IgM nuisance parameters, and we also marginalize over the spectrum of primordial perturbations. And this time the contours are color-coded by the version, the iteration of the emulator as we add more and more training simulations through the active learning. And the crosses are again the projected positions of the training simulations, color-coded by the iteration in which they are added to the training set. And the key point here is that as we add more and more training simulations, i.e. we go from the blue to the green contours, by the end of that process, there is no shift in the contours with respect to the addition of more training points. And that tells us we have converged estimation of the posterior with respect to the training set. So this is then our final summary exclusion plot. So here each line indicates the axion dark matter mass excluded by a given experiment, and our exclusion is given in green. This corresponds to a 95% credibility lower limit of 2 × 10⁻20 electron volts. And in fact, this improves by about an order of magnitude over the previous equivalent bound using Lyman-alpha Forest data. And we now very strongly rule out this canonical range of axion masses that I motivated at the beginning of the talk on the order of 10⁻22 to 10⁻21 electron volts. So what is driving this improvement in the bound? And in particular, we had access to new data, new measurements of the Lyman-alpha Forest flux power spectrum, which is accessing smaller scales than ever previously used for dark matter bounds. So this plot shows our data set, the flux power as a function of wave number k in 3 redshift bins. And the line overplotted is our maximum posterior model, and you see that we have a good fit to the data at that point. And then in maroon, I've illustrated the smaller scale that was accessed in previous studies. And so we have access to all these additional small scale data bins. And we carried out a test where we iteratively removed the small scale information, and we found that our axion bound weakened as a consequence. And what this is telling us is that by having access to smaller scales, we were able to rule out the presence of a cutoff from heavier axions, and so we improved our lower limit as a consequence. And finally, I'd like to say that the way we constructed the emulator was not only specific for the analysis of ultralight axion dark matter, but in fact could be re-optimized for the analysis of any dark matter model that induces a suppression in the linear matter power spectrum. For example, warm dark matter and various classes of interacting dark matter. And that's the focus of future work. So I'll just finish with my summary conclusions. We set a new 95% lower limit on the axion mass at 2 × 10⁻20 electron volts, which strongly rules out the canonical range of masses considered in the literature. Presented the active learning and emulator methodology, and this framework is able to test other dark matter models. Thank you for listening, and goodbye.